afternoon to everyone present over here. So me along with Harsha is over here to present before you a real-time project, data science project on predictive analytics for depression in diabetic patient using mobile sensor variable. So this is just basically a project which is done as a part of our PGP-BABI program along with Touchkin in collaboration with Apollo. Before I get into detail with the problem statement and the solution we provided for this, let me take a step back and share the global prevalence of diabetes worldwide shared by World Health Organization in 2016. So this is a global report on diabetes which is shared by World Health Organization in 2016. With this report we can see World Health Organization has said that there has been a significant rise in the people who have been diagnosed with diabetes from 1980 to 2014. The number has risen from 108 million to 422 million adults. Along with that, WHO also shared one piece of information that 1.5 million deaths in 2015 was caused by diabetes, with an add-on of 2.2 million deaths caused by increase in blood glucose level. WHO also projects that by 2030, diabetes will be the 7th leading cause of death. It is generally seen, there is a common pattern which is seen for all the people who are suffering from diabetes, that they have a very unhealthy diet, their physical activities is very poor. So if proper treatment is not given to diabetic patient on time, it can lead to severe consequences. It can lead to untimely death, it can lead to failure of multiple organs and many more health issues. As a suggestive action, what we suggest that they should have a good diet, they should have a good physical activity, they should have a regular screening of their blood glucose level, they should do a constant checkup. Now, let me get into detail of 3 Ws and how related to our project. So as I said, this project is done as a part of our PGP-BABI program. Touchkin was the company for whom we have done this project. It's a startup company which is basically based on healthcare. The next is what? Now, here we have 2 snippets. Now, when we are saying depression with respect to diabetes, I am not referring over here the clinical depression. When it comes to depression with respect to diabetes, we have a separate term for that, which is known as diabetes-related distress. Now, what is the difference between a clinical depression and the DRD? If you see, a clinical depression is a mental disorder where a person undergoes a torrent of sadness, a guilt feeling, a feeling of hopelessness. But in DRD, if you see, the person has some emotional burden. You know, when a person is diagnosed with diabetes, it is not a normal thing. They have to undergo a lot of regimen-related issue, they have emotional burden, they have physician-related issue, they have the social burden, lot of complication comes into their life, and it is not a easy way to tackle up all those problems. They go n number of hassles in their life. So the impact which a clinical depression and a DRD takes place on the patient is totally different. As a part of depression, the person can have an overeating habit, they might have a disturbed sleep. But with respect to DRD, the after effect is something different. The first after effect which we have is like the patient blood glucose level increases to a great extent, because of which the condition can deteriorate. So that is why we are taking into consideration DRD, not the clinical depression. The next is why. Why are we focusing on DRD, why not on depression? As I said, that DRD is an issue where it closely associates a patient's blood glucose level. It is the way by which a person manages their diabetes. The person doesn't take care of their diet, they are not involved in physical activity, they try to cut off from the social world. The after effect is that the blood glucose level rises to a great extent, and that's why DRD is very important. Now, how will you get to know that the patient is having a DRD? How will you know that the person is not having a clinical depression and he or she is having a DRD, diabetes related distress? We don't have a medical instrument by which we can actually calculate the DRD, but yes, we do have a manual process by which the DRD can be predicted. So what happens when a person is diagnosed with diabetes, they visit a physician, They share their experience, they share the problem which they face. The problem can be with respect to their diet, that problem can be with respect to the regimen, that problem can be with respect to the doctor or the physician. Maybe the physician is not able to give them the proper details with respect to the disease they are facing. So at that time what happens, the patient interacts with the doctor and doctor gives them a set of questionnaire. We have a snippet of that. So you can see these are the small snippet of the question. There are n number of questions actually. We have just shared a small snippet of that. So these questions are basically focused on different areas. Like it can be with respect to the emotional burden they are facing. It can be related to the physician, that the doctor is not able to help them out. It can be related to the regimen. It can be related to the social network or the support which they are getting from the peers around them. So once the patient is asked to score all these questions, like how much these issues are bothering them on a day-to-day basis. It cannot be true for them, but it can be bothering their day-to-day activity. Once they score all these questions, they get a final score, which is known as the DRD score. And as per the doctor or the medical science, what they say that any score which is greater than 4 is generally treated as very severe. So the person is considered to have a diabetes related distress. And any score which is less than or equal to 4 is considered to be normal. We can take it that person is all okay. So over here what we are trying to do, that since it's a manual process and at times the patient themselves, they don't know that they are having a distress. They might be under tremendous pressure, but they don't visit a physician, maybe due to lack of support, they don't visit the physician. So what we are trying over here, we are trying to bridge this gap by which we can create a model and we can predict that, okay, fine, this person can become prone to depression in time to come using the mobile sensor variable. We will not go with the normal manual process where the question is posted to the patient and they have to answer it. So with this approach, we'll be trying to build a model where we can predict the depression for the diabetic patient. So as a part of this project, we had 4 goals. The first is collecting the mobile sensing data with Touchkin in collaboration with Apollo. The second was to build a predictive model where we can predict the depression for the diabetic patient and we can classify a depressed patient from a non-depressed patient. The third is analyze the factors or the predictors which can impact the depression. Finally, to predict the probability, like how prone a person can be to a depression. We followed the Triste Method, which is the cross-industry standard process for data mining. The first is the business understanding. We tried to understand the business problem, which was shared with us by the Touchkin. We had the data, which we captured from Touchkin. Next is data preparation. The data preparation is the step where we had spent maximum time. 80% of our time of the project was spent in data prep. Finally, the modeling and evaluation and the deployment. So we had the data, though initially, in the initial round, we had lots of data, but the data which was taken by us for the model building, it was from December 2016 to February 2017. Now, as I said that we are using mobile sensor variable. Now, what do you mean by mobile sensor variable? These are the variables which, we are trying to understand a patient's behavior, a diabetic patient behavior. First of all, let me tell you one thing. All these patients are diabetic. So we are focusing only on the diabetic patient. None of the patients are like that who don't have the diabetes. So we are trying to understand how these diabetic patients are interacting with the world around them, how they are connecting with the social world. Now, to understand that, all these mobile variables, like social networking is one of the variable where we have the call related information, like how frequently the patient is interacting, how frequently they are calling, what is the call duration. The second is the location, like what is your traveling behavior, how frequently you are traveling your home, how much time you are spending at your home. Mobile usage and sleep is another variable where we are trying to understand how you are using your phone, how much time you are spending at your phone. Your phone is in a locked state or it is in unlocked state, your phone is stationary or it is movement. So all these variables, somehow they are trying to get you in structure that, okay, fine, this person is behaving in this way with the social world or the peers around him. The data is restricted for Indian population. So all these data were collected with the help of StayClose. StayClose is an app which is developed by Touchkin, and this app is installed in the patient's mobile device, and they are asked to keep their Wi-Fi and their GPS on so that all these variables can be captured through the app. Visa is a chatbot by which, as I said, that the patient is given a DRD questionnaire where they have to answer it. So the chatbot is able to get the response of the questions which the patient is giving. This is the snippet where we are trying to get, where we try to explore the data. We had around 215 metrics. Over here, it was not possible to showcase all those variables. We tried exploring the data, and what we saw that this 215 metrics, they were highly correlated with each other. So when I say highly correlated, what I mean that there were few variables which were redundant. We just need to club up and create a factor out of them. We don't have to use all those variables. So we had, at the down you can see there are some correlation plot. So all these variables, we had around 20 to 25 variables under each of the global variable, and there was a heavy correlation between them. So with this, we get a glimpse that, okay, fine, we don't have to create a model out of 215 variable. What we can do, we have to do a dimension reduction, a factor analysis by which we can reduce the 215 variables to n number of factors. Data prep is the part where I said we have spent almost 80% of our time. So initially, it started like we got around 20K data points with 215 metrics, but the data which we got, it was a very messy data, it was very noisy, it had lot of missing information. Only 5549 data points were there where we had the DRD labels. So when I say DRD label, means the patient has responded to the questionnaire, the DRD score is generated, and we are able to get the DRD label for this question. Remaining all 1400 around data points, they didn't have the DRD label. So we have to drop all those data points. Next, we whatever 5549 data points we had, there were only 455 records which had the complete set of information. So all the 215 metrics had the information, but remaining 5004 records, they had partial set of information. So there comes the missing imputation. We did the imputation for all these missing records. The missing imputation was the part which took a lot amount of time because we had to get in touch with the business to understand how should we impute all these missing values. Once the missing imputation was done, we had 5549 data points with 215 metrics, but building a model out of 215 metrics was not computationally effective. We can't go ahead with that. And since there was a heavy correlation between the variables, so what we thought that dimension reduction is the first step which can go ahead with. So we took factor analysis into consideration, and finally from 205 metrics we came down to 24 factors. So this 24 factors, when we put into the model, it was obviously computationally very effective, and it was very easy to analyze these 24 factors. These 24 factors, they started from your mobile being stationary. The one factor was like how your phone is getting, phone is behaving, like whether it is in a stationary state or whether it is in a movement state. The second is like how frequently you are operating your phone. Is it in a locked state or is it in an unlocked state? What is the call duration? What is the location? So all these are the factors which we have used to understand how the person is behaving, how a diabetic person is behaving with the world around him. So the next few slides, which is the factor analysis. So once we created the factors, we have to make it sure that there should not be any heavy correlation between the 24 factors. Because if there is a heavy correlation between the factor, we again need to reduce that further. So this was the correlation plot which we created once we had 24 factors in our hand, and we got to know that the correlation was very less, almost it was reduced to a great extent. The next slide is with respect to model building. Harsha will take over the next few slides. Thank you.
I hope I'm audible. Okay, thank you, Shweta. So far we understood that what type of data transformations we did, what is the problem understanding, and how we can, from a business problem transforming to an analytics problem we did so far now. Now the next step is to understanding how data science algorithms can be applied and make inferences. So these are the different layers of analytics now. So our hypothesis is that these parameters do not have any impact on the depression level. Now the alternate hypothesis made is that at least one of the factor is having impact on them. That is what hypothesis we are working with. Now these are the various steps we followed in the data processing. Some of them are like data sufficiency, like finding out how much data is appropriately useful data in terms of rows and in terms of matrix. And dimensionality reduction, as just now Shweta mentioned, factor analysis reduced to 24, which are actually uncorrelated. It reduced almost more than 80% correlation of data got reduced. And then we made sure that we did a cross validation and using the training and test with a 70 and 30 ratio. And we made sure that the computational effectiveness is there. And the set of models we use these are the ones: logistic, CART, random forest, neural support, and gradient XGBoost models. Some other things which we did is that we made sure that the test and train are actually preserving the ratio of train and test, the ratio of yes and no labels across the data sets. And let me go through some of the good models, some of the best models which work well out. So random forest is one of the model, which is a bagging algorithm. In simple words, is more like a number of decision trees combined together and to frame a final decision. So the fundamental concept of random forest is actually try to reduce the variance part, and we could see that number of nodes, number of trees at a given node, and how is the OOB error, out of object OOB error is there, we try to validate, and these are the kind of metrics we observed. So you can see that actual is 1 and 0. 1 means somebody is under depression, 0 means somebody is not under depression. Similarly, when we are predicting how the numbers are matching, and we came up with the metrics such as sensitivity, specificity, accuracy, and miss rate, what is the cost involved, all these are things. We could observe that the accuracy in train and test, they both are real, almost close by. So it actually variance part it took care of. Because some of the models like logistic regression, we could see that train error is very less, but test error seems to be not that less. The gap is higher. And then these are the ROC curve lift, how much lift it is observing from the default 45 degrees line. We could observe that this is one of the best model, 94% accuracy we could reach. Some of the strengths we could observe this way. It is a robust model in spite of so much of noisy and outliers data. And it reduces variance, at the same time takes care of overfitting scenario. And we could actually identify which of the key variables are causing or having higher impact on the depression is something we can identify from the variable importance plot. And the other side is, which is the negative side, is that there is some kind of complexity involved while picking up the set of decision trees, which trees to pick, how many trees to pick. That is a gray area. We'll have to take a call based on the context, based on the data and all. And it can be sometimes bit slow as the complexity of number of metrics goes increasing. And I would like to mention some of the other models we experimented. One of them is neural networks and the other is supporter vector machines. So neural networks, it works well when the data is in an enriched format. In the sense like if you have very limited noisy data or missing data, it works well. The moment the noisiness is very high, it is not a right model or best model to pick up. And we could see the supporter vector machines. This is very well works. It is one of the good model to work in a high dimensional space. When the number of dimensions are more than number of samples, this is one of the better model compared to other models. In simple words, supporter vector machines is basically like in an n-dimensional space, we are trying to segregate into two classes, wherein segregation should parameter tuning happens on cost and gamma parameters to identify the best outer boundary line. And let me get into some of the boosting algorithms we work with. So boosting algorithms are more like working with the, in a sequential manner, we try to correct the previous tree errors. So it's like initially first we start with one set of trees, and whatever the errors, weak learners, we try to empower them, giving higher weightage to them. In a number of iterations, we can converge to a stabilized state. The gradient boosting and XGBoost, the major difference comes with the parallel processing. Because in boosting, it's more of a computationally, it is an expensive one because it is a sequential error correcting algorithm. Whereas the XGBoost, on the other hand, it takes care of the time and computational effectiveness. So it does parallel processing. That is the best part of it. And it also takes care of the regularization to control overfitting. So one of the best models are, we could observe that one is the random forest and is the XGBoost. These are the ones. And in our observation, we could see that model complexity, train and sample, as the model complexity is increasing, like high bias and low variance to low bias, high variance. Most of the bagging models are on the left extreme, boosting models on the right extreme. We'll have to pick a balance point which is the best fit, because you can't expect a test sample to be having higher error. So you should take a middle area which is a trade-off between both sides. And then what we have done is that, so far we have done some kind with a data imputation. Whenever there is a data is missing, we try to impute with the median or average based on the metric context. Now we did a, without any imputation, how the model is working, we try to test with. So we could observe this, that most of the times the performance metrics are on the similar lines on the, with a new data set and all. So even we could see the performance metrics are with the new models, it is coming this way. So let me explain what is the way we evaluated our models are based on this thing. One is that a gap between train and test accuracies. Are they standing with a new, completely blank new data set? Is the performance matrix standing at the same level or not? And higher sensitivity and higher accuracy and all other metrics such as miss rate, standard error, computational resources, time complexity, we are aiming to reach at a minimal level what it can do. And this is the performance metrics across all the models. We could see that random forest and XGBoost are standing, next SVM are standing at a best level. And next step is that we identify which are the set of variables are having positive relationship and negative relationship with depression. We could observe that some of the examples this way. Screen on during active hours. So our variables are split into morning 9 o'clock to till 8 o'clock. How much time the mobile is switched on, and that means the person is very engaged with the virtual world. He is very connected to the mobile world and very completely away from the real world or in-person world. So there is it is having a higher positive relationship with depression. And then stationary during positive personal hours, call spread during peak hours. So like night 9 o'clock, 10 o'clock till morning 8 o'clock, if somebody call spread is very high, that means somebody is working at night 11 o'clock, 12 o'clock or 1 o'clock, there is a higher tendency, we could see the person is getting into depression and all. On the other hand, we could see negative relationship with the below 3 set of variables. That is on the contrary example, these are the ones. And what we have done is that we have listed down all the variables, and across all the models, what is the ranking of the each variable, and based on that we identify the green colored ones are the ones having positive relationship and the red ones are the ones having negative relationship with the depression levels, DRD score levels. So our model, we could observe that some of the strengths are this way. In spite of so much of noisy and missing data, we could still stand at a stage of 86% of accuracy. So that is one of the best part. And our cost benefit analysis, so like the miss rate, how much is the cost it is incurring, we try to calculate, and we could see that this is actually causing less than 12% of type 2 error, and it's one of the best as compared to the existing scenarios is much better than them. And in terms of weakness, we could observe that mobile signals, we are assuming that they are very natural, not like altered or anything like that, not just for the sake of any purpose, anything like that. And lots of significant variables, there is a overlap with the some gray area is observed, in the sense like same variable having a overlap with on the secondary both sides of the boundary lines. Some of the opportunities we could see is that patients' clinical data could have been added much more value, in the sense like BMI value, height, weight, what kind of cholesterol related, heart, BP, blood pressure, sugar levels, these are the other information could have been added. Unfortunately, Apollo was not ready to share such kind of sensitive data, so at the moment we work with only mobile sensors data. And threats, when it comes to it, is more like building the model with the less data variation. We are assuming it is a larger sample population is a representative, but if there is a altered data, then it is going to be a threat kind of. We are actually, it is giving wrong symptoms, wrong signals. So our observations seems to be like, these are the ones. I already spoke about accuracy and miss rates. Some of the observations are this: human and social sciences area, typically the data tend to be like lot of missing data will be there. The nature of data is like that. If you look at finance data or marketing data, you will have plenty of data, and you can make a lot of judgment, better decisions and all. Whereas human and this kind of information, you will always see a sense of missing data. And we could see that people who are very highly connected to virtual world, there is a tendency they are getting into depression. And we actually try to find them into segments kind of, people who are working and what kind of depression level. Let's say some female housewife and not working, not connected to any world, so such kind of what kind of depression. These are the type of segments work we could do it. Some of the recommendations we could see is this way, like patient's habits we try to analyze, and in terms of heart rate, sugar level, sleep cycle, blood pressure, these are the kind of information we gathered, and we try to make recommendations on top of it. The key challenges involved are this way. One is the technical challenges, second is the regulatory. Technical is more like how do you handle a missing data, that is one of the challenge. And we are considering a missing imputation with the average or median. Regulatory challenges are more like how you gather the real data from Apollo Hospital is there. The data is very confidential, sensitive data. We should not have the patient's name. We have only the ID number only. So such kind of things. And future steps are like data capturing at the moment is happening at from 6-hour level. Instead, if it happens at a much granular level, such as 1-hour level, data can be much more refined, and you will get a much more better approach. And the mobile app, the one which you saw earlier, Visa and Touchkin app, it actually alerts the physician and makes a suggestion that this specific patient is potentially under depression. So there is a way to tackle that in an automated alerted way. And these are the set of testimony we have received from our client, Touchkin. These are the ones. That's it. That's all I have for today.